So remember, mainly when you are talking about solving a system of equations, you can use the graphing method, the substitution method, or the elimination, also known as the addition method. So those are mainly the three types of methods we apply when we're trying to solve a system of equations. So when we're talking about a system of linear equations, of course, we're talking about you will have equations which are going to be in the linear format. So, in the standard form, that would look like ax plus by equals c, or if you put it in the slope intercept form, it may be in the form of y equals mx plus b. So your basic, linear equation in two variables. Now, if we put two or more of these equations together, of course, then we end up calling them as a system of equations. And when you are trying to find the solution for the system of equations, remember that it has to satisfy both the equations in your system. So that solution set, make sure will satisfy both the equations in your system. So let's take a look at a quick example here with the graphing method. So if you are talking about graphing, then, of course, use your slope and the y-intercept to graph both the lines. And normally when you are talking about two straight lines, these are the cases you are looking at. So you can have either the two lines which will intersect exactly at one point. And so, of course, if they are intersecting exactly at one point, that point of intersection will end up becoming your solution set. So in this case, we would say we have a consistent system and our equations are independent, and you have exactly one solution. And like I said, basically that's going to be that point of intersection, and that becomes your solution set. Now, as you can imagine, the way the two lines are, they are going to end up having different slopes. So that's case number one. Then you can have where basically the two lines end up becoming the same line. So that is what we call as overlapping lines, or, like I said, they can be the same line. In that case, every single point that is going to be on your line, because it's going to be common between both the points, you actually end up having infinitely many solutions. So this one here, we say it's a consistent system. However, your equations are dependent because, basically they're the same equation, and you end up having infinitely many solutions. So in this case, obviously, since both the lines are the same, they will have the same slope and they will have the same y-intercept. So that's case number two. And then the last one, you will actually end up where the two lines are parallel to each other. So kind of like, your railway tracks. So they are never going to touch each other. They are never going to intersect. And if you have, if you don't have a single point, which is common between both the lines, then obviously that means we have no solution. So in this case, we would say we have an inconsistent system. And even though the two lines are parallel, remember that means they will have the same slope, but obviously they will have different y-intercepts because, they're going to cross the y-axis at two different points. The same slope, but different y-intercept. So basically, these are the three things that can happen. And it doesn't matter if you are using the graphing method, if you are using the substitution method, or if you are using the addition or the elimination method. The three cases are always going to stay the same. So are the lines intersecting? Are they the exact same line, or are they going to be parallel lines? So that's kind of where, we try and use these different methods. So like I said, let's do our graphing one here, just so you guys can kind of see what the graphing looks like. So in this case, we can identify what our slope and y-intercept is going to be for each of the lines. And then using that, we can go ahead and graph these. So looking at that first equation, y equals x minus 2, what do you think our slope and y-intercept is going to be for the very first line here? So y equals x minus 2. What's our slope? And what's our y-intercept? And same thing for the second line. So you can either unmute your mic and tell me, or you can put the answer in chat, whatever you're comfortable with. Alrighty, Genevieve, I see you've got slope equals 1. Very good. That will be y-intercept of -2. So y-intercept obviously means your x value is 0 and the y value is -2. All right, very nice. And then for the second line, guys, what will be our slope and y-intercept? Very nice, Diego. Yeah. So our slope is going to be -1 because you have the negative x. So -1, and your y-intercept again, x value is 0 and y will be +4. So obviously you can see both of our lines have different slopes and different y-intercepts. So when you try to graph this with that first one, we'll start at 0, -2. And then using our slope of 1, you're basically going up 1 and right 1 because it's a positive slope. So up 1, right 1, basically, you can kind of keep going, or you can go down 1 and left 1, and obviously it will still be the same line. So as you can imagine, this is kind of what that line ends up looking like. So y equals x -2. Now for our second one, we are looking at a y-intercept of 0, 4. So that's 1, 2, 3, 4. And then a slope of -1, which means you go down 1 and you can go right, or you can go up and you can go left. So remember, one of those directions has to change. So negative slope, we will go down and still go right. So this is kind of what this line ends up looking like, or you can go up and go left. And this is kind of what this line ends up looking like. So this was our y equals -x +4. So obviously, as we saw that we had different slopes and different y-intercepts, you can see that our lines are in fact intersecting. So can you tell me at what point the two lines are intersecting at? What would that solution look like? So what would be the ordered pairs for that line, that point? Yeah, very nice, Jen, Della, Diego. Yeah, perfect, because you can see you are going out 3 units on the x-axis, and then we are going 1 up to the y-axis. Okay, perfect. And the quick way to check your answer and see if that is correct or not is obviously we put it back into the equation and we try and check that. So we came up with 3, 1. So if I put that, of course, x value is 3, y is 1. Let's put that in the first equation. So if y is 1, x is 3, 3 minus 2, of course, gives us 1. You end up with a true statement. So we know it definitely is a point on the first line. We can do the same thing for the second equation. So again, y is 1, x is 3. So you've got -3 plus 4, which also comes out to be 1. So you are getting a true statement on the second one also. And so that tells us our solution set is going to be that ordered pair 3, 1. And that's basically what they were telling us right over here, is that if you have 2 intersecting lines, you will end up with exactly 1 solution. And that's exactly what we came up with. So keep in mind, you can try the other 2 examples here in the handout, and it's pretty much going to be, one of them will be parallel lines, the other will be the same line. And again, these are done in the video lectures if you wanted to see that, but I'm just picking one example from each section. So now let's talk about how to use the substitution method to try and solve these equations. So again, you can see there are 3 examples here. Each one of them will give you one type of solution, but let's go ahead and use, I don't know, maybe let's do number 5 over here and let's see how the substitution method works out. Now, remember, guys, when we are talking about substitution, we are literally saying, let's take one equation and substitute it into the other one. So you take one equation and put it into the other one. So you either want to solve your equation for x or y, which means either get x by itself on one side or get the y by itself on one side. So the easiest one to rewrite for us here will actually be this first one over here. So you've got y minus 3x equals 5. So if you want to get y by itself, all you need to do is add that 3x and move it to the other side. And so as you can imagine, when we do that, you are left behind with y because that 3x will cancel out. So you're left with y. And then on the other side, you're basically adding 3x to 5. And you end up getting y equals 3x plus 5. So we can call this equation 1. This guy here will be equation 2. And what you're going to do is basically we are going to substitute equation 1 inside of equation 2. So we're going to take equation 1 and put it into equation 2. So what that ends up giving us will basically be where you see the term y, you are now going to replace it with 3x plus 5. So keeping my left-hand side the same, we'll leave it as 3 times in the parentheses x plus 1. And then where you see the y, we're going to substitute with that first equation. So this is where we replace the y or substitute it with 3x plus 5. And then remember you had that minus 2 at the end. So what the substitution does, as you can see, now this new equation that we came up with is all in terms of x, right? There's no y variable anymore. So we've taken it and converted into a variable, an equation with just one single variable. And now we can find out what the x value is going to be. So that's kind of what that substitution method does. So we just need to clean this up now. So we will start by the left-hand side, going ahead and distributing that 3 inside the parentheses. And then, of course, we'll clean up the right-hand side. So 3 times x, and then 3 times 1 will end up giving us 3x plus 3. On the right-hand side, we've got 3x plus 5, and you're really not multiplying anything into it. So just leave it as it is and then bring down that minus 2. So our goal is to get the x terms on one side and the constant terms on the other. So we can go ahead and add the 5 and the negative 2 on the right-hand side. Go ahead and combine like terms. So 5 minus 2 will, of course, end up giving us 3. So you should notice at this point, even though we haven't cleaned up our equation, that both sides of our equation are exactly the same. Even if you were to go ahead and clean this up, it would still show you same thing on both sides. So let's say we're moving this 3x to the left-hand side. And then we're moving this positive 3 over to the right-hand side. So even if you wanted to get the x on one side and the constant on the other side, you will notice that basically the x terms cancel out and the constant terms also cancel out, leaving us behind with basically 0 equals 0. So remember, as I said, you have the same term on both sides. And even if you clean it up, you will still continue having the same term on both sides. In this case, now your term just happens to be 0 and 0. So anytime you end up with a true statement like this, that actually means you are looking at the two lines being the exact same line. So anytime you end up where the left-hand side of your equation matches exactly the right-hand side, or if you clean it up like we did and you get 0 equals 0, this only happens when the two lines are exactly the same. And that tells us that obviously, you're looking at infinitely many solutions. So this tells us we have the same lines. And that means infinitely many solutions. Sometimes they will have you write the answer for the solution set in what we call as the set builder notation. And so that would look something like this, where you take your ordered pair x, y, and then use any one of those two original equations, doesn't matter which one. So you can do the first one, y minus 3x equals 5. So what this set builder notation is telling us is that whatever is the solution for this equation, y minus 3x equals 5, that ordered pair is going to be the same solution for your entire system. So this is what we call as a set builder notation. So you may see where MyMathLab will want you to put the answer in that set builder notation, or they may just have you choose the option that says infinitely many solutions. So that's why you should be familiar, just with both notations. So questions on this method here, guys, with the substitution method? Okay. Let's take a look at the addition method. And as I was telling you, some textbooks also like to call this as the elimination method. Because the idea here is by adding the two equations together, we are trying to get rid of or eliminate either the x or the y variable. So the idea is, how can we add the two equations together so either our x will cancel out or our y will cancel out? So that's why it's called either the elimination or the addition method. And let's see, which example do we want to do here? Let's try number 8, I think. And let's see what this one will either come out to be the same equation or parallel. I'm not sure. We'll have to break this down and see. So remember, the idea is, how can we add these two equations together? So the first thing you probably want to do is either rewrite the first one or the second one. So, we can kind of have opposite values on our x and y variables. So the goal we are trying to go for is you should have opposite coefficients either on the x or the y variable. So, if you have like +2 and -2 as your coefficients on the x value, then they can cancel each other out. Same thing for the y. So you're always trying to go for opposite coefficients on your variables. Just to show you, like in terms of the example here, you can see how you have 3x on this guy. So let's say if we were trying to add these two equations together, then we would want this one to have a coefficient of -3. So how would we achieve that? Or if we were trying to get rid of the y variable, if this guy is 2y, then we would want this one to be negative 2y, so that when we add the equations, we would be able to get rid of the y variable. So that means, depending on, are you getting rid of the x or are you getting rid of the y variable, you want to then multiply your entire equation by that coefficient. So in this case, we would probably go for the y variable, because you can already see we have opposite signs on the y. So this guy is positive, this guy is negative. To turn this into a -2y, we would basically take that first equation and multiply it by 2, which would then end up giving us 2x minus 2y, and then 5 times 2, of course, will be 10. Keep the second equation the same, and then now we would go ahead and add the two equations so that our y variable would end up canceling out. So that's kind of what you are trying to do with the elimination method. So if we just rewrite, we'll keep that first equation the same. So keep it as x minus y equals 7, but let's rearrange this guy. So you can see you have -x. Let's bring that to the front. This guy is +y, so let's bring him to the back. And then on the other side, your 5 will stay the same. So just by rearranging the two equations, you can see we already have the opposite, right? So if we go ahead and add these two equations together, you will notice, and we didn't even have to multiply by anything, just rearranging it did the job for us. So you've got a +x, a -x, you've got a +y and a -y. So they basically just end up canceling each other out, right? So your left-hand side, everything canceled, which means you end up with a 0 there. On the right-hand side, the 7 and the 5 are both positive, so we end up adding them together, but you will see they add up to 12. Now, we know 0 does not equal 12, which means we ended up getting a false statement over here. Now, if they were going to be the exact same lines, guys, you should have ended up with 0 equals 0 like we did over here. So if they were going to be the same line with infinitely many solutions, you should end up with 0 equals 0, and that's not what we have over here. So we know 0 does not equal 12. This only happens when the two lines are parallel to each other, which means they have the same slope, but they have different y-intercepts. So that tells us these are parallel lines, and parallel lines have no solution, because remember, these lines do not touch or cross each other. They will always stay parallel, and that means you will never have any common point between the two lines, so you have no solution. And so this is what would end up when you are looking at parallel lines. So sometimes you will say no solution, or we can say it's an empty set. And usually for the empty set, we either use this notation here, or sometimes we'll just use these brackets with nothing written in the middle. So any of these options would be okay for, saying there's no solution over here. So this was your addition or elimination method. So basically, like I said, the idea is you have to try and add the two equations in such a way that at least one variable is canceling out. So either the x or the y, it doesn't matter which one. And then whatever cancels out, then you go ahead and solve, what's left behind. So something like number 7 over here, you can see our positive 2y, negative 2y canceled out. If we add the remaining terms, you would end up with 5x over here, 20 over here. So now you have 5x equals 20. Divide both sides by 5, and you would end up getting x equals, what's that, 4. Now that you have your x value, you can go back and find the y. Use any one of the equations, it doesn't matter. I guess I'm just going to use that first one. You end up with x minus y equals 5. If x is 4, go ahead and find your y value. And basically, what will that come out to be? Negative 4. So this cancels out. You're left behind with negative y equals 1. Move the negative to the other side, and you get y equals negative 1. So in this case, your solution set is coming out to be 4 and negative 1. So in this case, you will see, since my x did not cancel out, we were able to go ahead and solve it. Whereas in number 8, your x and y both canceled out, and you got a false statement. In number 9, and again, you guys can see this in the video lecture, but number 9, they do actually come out to be the same line. So you will actually end up with 0 equals 0 when you try to, solve this equation. So that's kind of how each one of these methods work out. And then we just had included some applications just to show you how the system of equations can be applied to real life applications. So I would say, again, if this has been a while that you have done any of these system of equation type of questions, just look through the video lecture for 5.1 just to refresh your memory. But there is no homework, and you're not going to be tested on 5.1. Remember, guys, this is just a review section just to get you comfortable with the 3 methods of solving these. You are actually starting out with section 5.2 in your homework and your exam. But before we move on to 5.2, did anybody have any questions in just what we have reviewed so far? Okay, so let's see how we can use this in what we're trying to do. So we're kind of continuing that theme of working with linear equations, but you will see instead of 2 variables, we're actually getting into 3 variables over here. Della, so the 3 methods were the graphing method, the substitution, and then the elimination or the addition method. Okay. Now, the graphing method, and I know we've kind of talked about this over different chapters, we don't heavily rely on the graphing method because, you're not always going to get nice integer answers, right? You're not always going to get like 3 and -1 and answers like that. A lot of times we do actually end up with fractions and decimals as our answer. So normally I would recommend staying with the substitution or the addition method. For the simpler examples, graphing is okay. But for the most part, we want to try and use either the substitution or the addition method to solve them. And you will see once we get into like these system of linear equations with 3 variables, graphing kind of goes out the door because now you are talking, basically 3-dimensional. And it's really hard to visualize a lot of these, 3-dimensional intersections and, how the surfaces are interacting with each other. So we will primarily work on substitution and the addition methods over here. So one thing I did want to mention is even though we are calling these as linear equations, just keep in mind the graphs of these equations are not going to be straight lines. Of course, here in section 5.1, these were all straight lines because these are, your true traditional linear equations in the 2 variables. However, once we get into these 3 variables, you are actually not looking at linear equations. The only reason we call them linear is because they look very similar to the linear equations in 2 variables, but your graphs are not going to be straight lines here. So a linear equation in 3 variables, x, y, and z, is going to have this form: ax plus by plus cz equals d, where a, b, and c will be, of course, your real numbers, and we don't want all 3 a, b, and c to equal 0 because, if each one of these numbers are equal to 0, then your variables x, y, and z will all disappear, and obviously we don't want that. So just an example of what this equation might look like. Now, since you are looking at 3 unknown variables, instead of an ordered pair, you are actually going to have an ordered triple, which will, of course, have the form of x, y, and z. So that's how we would write our solution sets, as these 3 numbers for x, y, and z, kind of the same way as we write an ordered pair, but instead of a pair, you will have 3 numbers in there. So just some examples of, if you try to find the solution for this equation, these would be some of the solutions that you would end up with. Obviously, you are going to have infinitely many ordered triples that would be considered as solutions for these equations in 3 variables. Now, the other thing, like I said, it's kind of hard to visualize what these, graphs, I guess, will look like. But basically, the thing to remember is this is going to be a 3-dimensional coordinate system where your third axis will basically become the z-axis. And obviously, the idea is your z-axis will be passing through the origin of your x and y plane. So, imagine this is your x-axis and your y-axis. So, think of them as being flat. Let me see if I can grab some pens over here. So basically the idea is think about your x and y axes, being like this, like we normally have it. So, at a 90-degree angle from each other. And then when you bring your third dimension, the z, you kind of think of it as being something like this. So, it would be vertically intersecting them. So your x and y are basically going to be flat, because that's 2-dimensional. And then when you bring your third dimension in there, it's going to end up looking something like this. Okay, but again, trying to draw a 3-dimensional image on a 2-dimensional paper or, screen like this, again, you kind of have to think about how it's going to be placed. So basically, your x and y are placed horizontally, and then your z-axis, as you can see, is placed vertically. So that's kind of how this works out to be. Now, when you take your equation and try to graph it, it actually ends up looking like a plane. And the idea is your graph is going to be a plane and basically not a line, as I was saying. It's called a linear equation, but you don't have a single line. You want to think of this plane as an infinite sheet of paper, which basically has no edges, because the idea is, just like your line keeps going in both directions, the idea is if you have this infinite sheet of paper, it's just basically expanding, all over. It's just going to keep going, in all directions, basically. And that becomes difficult to draw. So the closest thing we can draw a plane is something like this, and that obviously does not look like an, infinite sheet of paper. So that's kind of why graphing, as you can imagine, is not going to be a recommended method, for solving the system of equations. So basically they're saying one way to draw a representation for the plane would be to draw a triangle whose vertices basically represent the point of intersections, where the plane meets the axis. So basically we know this would be kind of what you would think of the y-intercept. This would be the x-intercept. This would be the z-intercept. And you're basically just drawing, those as the vertices of your triangle. And that's the best thing you can do as far as drawing your graph goes. I believe, if I remember correctly, did I time out of this? No, I'm good to go. Okay, so basically the idea is, how do we solve a system of equation, that kind of looks like this? So you can see the graphing example if you wanted to, but you're really not going to have a graphing example in your homework, if I remember correctly. So let's get into how to solve the system of equations. And this one here is just kind of talking about what I just said, how difficult it is to imagine, like if you have 2 or 3 planes together, how exactly are they intersecting? Can you find a single point of intersection? Are they intersecting along a side? What kind of configuration it has? It becomes very hard to kind of imagine something like this. So we are going to stick with substitution and addition method over here. So this one is talking about what would an independent system look like. Now in 2-dimensional, your independent system is basically something where, the 2 lines were intersecting and you had exactly 1 point of intersection. So when we try to translate that into a 3-dimensional image like this, what does it end up looking like? So this is talking about if you have a linear system with 3 variables, it can have 1, infinitely many, or 0 solutions. So the idea is, if your 3 equations, which represent 3 planes, if your 3 equations corresponding to 3 planes intersect at a single point, then we basically say you have 1 single solution and your system will be considered as being an independent system. So if you just have a single ordered triple where the 3 planes are intersecting, but they literally only meet at 1 single point, then that becomes your single solution, and we will say you have an independent system over here. So they're talking about like how to solve this, but before we get into the solving part of it, let's take a look at just how to check an answer to make sure we have a solution to our system or not. So you will see over here, guys, they're giving us the ordered triple, and they're asking us to determine if this is a solution or not, yes or no. So let's take a look here. So remember, your ordered triple is 5, 1, -5. So of course, it's in the alphabetical order. So this is X, this is Y, and this is Z. So you're going to check in each of the equations and see if it satisfies that equation or not. So let's start with the first one. You have X plus Y plus Z equals -9. When you replace your X, Y, and Z, do we get a true statement or a false statement for that first one? So X plus Y plus Z, what will this add up to on the left-hand side? Yeah, Della, very nice. So as you can see, you've got a positive 5 and a negative 5. So they will obviously end up canceling each other out, leaving you basically with just 1 behind. And you are ending up with 1 equals -9, which obviously we know is not true. So we are getting a false statement over here. And honestly, you don't need to go any further than that, because if you already got false on the first one, it doesn't matter if it checks out with the other two, right? It doesn't work on the first one. So this one, of course, is then telling us, no, this is not a solution to the system. Now, if you got true on the first one, then obviously you want to keep going, because then you're not going to stop. So just because we are here, let's go ahead and do a quick check, but we know our answer is going to be no for this equation or this system. X minus 2y minus z equals 8. So x is 5 minus 2 times y is 1 minus from the equation, and then the z also is minus 5. So you should have 2 negatives here, which would become 5 minus 2, and then negative times negative is positive. And here you will see 5 minus 2 is 3, 3 plus 5 is 8. You get a true for the second one. And then let's see for the third one, 3x plus 2y minus z equals 22. So again, our x is 5. Y is 1, and same thing, you have negative from the equation and then negative from the number. So 3 5s are 15, plus 2 times 1 is 2. Negative negative becomes positive. And so you can see 15 plus 2 is 17. 17 plus 5 is 22, and you actually ended up with true on the last two equations, but because it failed on the first one, it is still not going to be a solution. So you have to get true for all three equations for it to be a system solution. Does that make sense? Yeah. So make sure if you don't get true on all three equations, it is not a solution to your system. And so that's where this guy comes out to be. Okay, now we are getting into how do we solve the system of equations. So we definitely want to look at the instructions for this one. So as you can see, they are talking about you need to reduce your system to break it down into only 2 equations with 2 variables. So instead of having 3 equations with 3 variables, you want to break it down to 2 equations. And I'm just randomly using letters over here. But you need to break it down with 2 equations in 2 variables. Now they can be x and y, they can be y and z, they can be x and z, doesn't matter, as long as you have only, it can be with z, like I said. It can be y and z, it doesn't matter. So it can be y and z, just any combination, but just 2 variables, 2 equations. Then they are saying, look for the easiest variable to eliminate. So you can again use the addition or the substitution method to do that. But, break it down into where you only have 2 of the original equations left behind. Okay. And then, of course, the idea is you can choose to eliminate the first and the second, or you can choose to eliminate the second and the third, or you can choose to eliminate the first and the third equation. So you can do whatever combination you think will be easier to work with, and which will help us get to our answer in a more straightforward way. Once you have broken it down to 2 equations and 2 variables, then just like we did in section 5.1, you can use the substitution or the elimination method to try and figure out what those 2 variables will be. Once you have solved that system, then come back to one of the original 3 equations and then find your answer for the third variable. And once you are done with all 3 answers, for your x, y, and z, then basically we go back and check all three of those answers, your ordered triple, back into the original system to make sure, you know, we are able to solve and get a true statement for all of them. So that's where we're going to use this example to help us out. And let's actually do this in our notebook because we'll need a little bit of space. So you guys may want to get like a fresh piece of paper because this does take a little bit of calculation to work through. So we'll need some space for this. So let's take a look here. This is question number 2, 5.2.17. Alrighty, so our system is 7x minus y plus z equal to 5. Let's call this equation 1. We've got 2x plus 2y minus 3z equal 26. Let's call this equation 2. And then for the last one, we have x. Oh, why is it doing this? Okay, not sure why it's trying to overwrite itself. Okay, 2x plus 2y minus 3z is 26. And then the last one is x. Oh, Lord, I'm not sure why it's doing that. X minus 3y plus 2z equals negative 21. And this will be our equation 3. So the first thing we need to see is, okay, which variable is going to be the easiest for us to eliminate. So remember, you can do this in the combination of the first and second equation, the second and the third equation, or the first and the third equation. So, you know, whatever combination will work out in the best way. So I'm looking at, you know, our y variables. You can see some of these have negative coefficients and positive coefficients. Same thing with z. Some of these have negative coefficients and positive. However, all of your x values are all positive numbers, right? Positive 7x, positive 2x, positive 1x. So it might be easier to either choose y or z to eliminate. Okay, so Della, you are suggesting that we use 1 and 3 and multiply the first equation by 2. Okay. You will actually, yeah, that will work. The only difference would be, Della, to multiply by -2 instead of +2 because you do need opposite signs. Yeah, so let's do that. We can start by taking so that would mean we would take the first equation and multiply it. Multiply equation 1 by -2 and then add it to equation 3. Alrighty, so let's take a look at that. If you're multiplying the first equation by -2, what will we end up with on that one, guys? Because you're multiplying the entire equation, so from the left all the way to the right. So what will that new equation look like once we multiply equation 1 by -2? All right, Della, you've got 14x plus 2y minus 2z. So shouldn't that be -14x because you're multiplying by -2? Yeah, so be careful with those signs, guys. So you are taking 7 times -2, which will give us -14x. Oh, I don't know why it's doing that. This is so annoying. Okay, negative 14x, and then negative and negative becomes positive 2y, negative 2z, and then you had negative 10. So yeah, that works out fine. So you're taking that, but remember, you're leaving the third equation as it is. We're not changing it. So that will be x minus 3y plus 2z equals negative 21. And we'll actually go ahead and add the two equations at this point. And as we did this, obviously our goal was to eliminate the z variable. So your negative 2z, positive 2z cancels out. So that might be something to mention here because you are eliminating z. Alrighty, so let's see what we are left behind with. So negative 14 plus 1 in your x variables will end up giving us negative 13x. Combining the y variables, you've got plus 2 minus 3y, which will of course end up giving us negative y. And then on the other side, of course, the z canceled out. The other side, you're adding negative 10 and negative 21, which will of course end up becoming negative 31. So this now we will call as equation 4. Okay. So we have one equation with two variables. Now we need to repeat the process. So you can either use equation 1 and 2, or you need to use equation 2 and 3. So which combination do you think will work out better, 1 and 2, or should it be 2 and 3? To find our second equation with the two variables. And again, you are trying to eliminate z since we eliminated z in equation 4. So which one do you think will be easier so that we can eliminate, from equation 2, that z variable? Yeah, Della, very nice. Equations 1 and 2 will again work out really well. So now we want to get rid of the negative 3z, which means what do you think we should multiply equation 1 by so that we can get rid of that negative 3z? Yeah, you will actually multiply by 3. Very nice. So now when you're combining 2 and 3, we will be multiplying equation 1 by a positive 3 now. Yeah, very nice, Della Maria. Good job. Okay, so let's see what that will look like. So we're multiplying that first one by 3. So that will be 7 times 3, 21x. 3 and negative y would be negative 3y. 3 and z, of course, will be plus 3z. And then on the right-hand side, you're multiplying 5 times 3, which will, of course, give us 15. We're keeping the second equation as it is, so that is 2x plus 2y. And negative 3z equals 26. All right, so again, we are now adding these together. And basically what we did here was multiply equation 1 by 3. Then add it to equation 2. Okay. So now, as we were again hoping to get rid of the z variable, we did. So we have eliminated z. And let's see, 21 plus 2 will end up giving us 23x. You've again got negative 3y, positive 2y, which will end up giving us negative y equals, and then let's see, what does this guy come out to be? 6, 11, what is that, 41? And let's call this equation 5. Any questions up until now? So we have now taken our system of equations, which had three equations, three variables, and we've broken it down into two equations with two variables because now we can put 4 and 5 together. So you've got negative 13, sorry, that should be x minus y equals negative 31. This is our equation 4. And then we have 23x minus y equals 41, which is our equation 5. So between the x and y, which one do you think will be easier to eliminate? The x variable or the y variable? Which one would be easier for us to get rid of? And how would we get rid of it? Okay, you guys are saying y. That's fine, Diego, Della. How should we get rid of y? What kind of calculation would we need to do? Because right now my y does not have opposite signs, right? We need to make that into opposite signs. So what should we do? Yeah, either equation 1 or equation 2, whichever one you want to multiply with, multiply it by -1. So let's go ahead and take just the first one and multiply it by -1, which will then end up giving us, let's see, basically all the signs will change. So that becomes a positive 13x, positive y, positive 31, and then keeping the second equation the same, 23x minus y equals 41. And then when you add this together, your y should cancel out and you should be able to find a value for x. And what do you think that x value will come out to be? So clean that up and let me know what you're coming up with for your x value. Yeah, very nice. I see Maria, Jen, Della, very good. Yeah. So this will add up to, let's see, 36x. Y is gone, and then this is 72. So when you try to get x by itself, you divide both sides by 36. And of course, x will come out to be 2 because 36 times 2 is 72. All right, so we've got one variable down. Now we need to find y and z. Now you have to go with y first because you will either use equation 4 or equation 5, any one of those to find the y variable. So finding y, I guess it really doesn't matter, but I'm going to use equation 5. So that's 23x minus y equals 41. And then, of course, our x value is 2. So what will that y value come out to be in this case then? All right, Della, I see your answer. Let's see what the rest of you are coming up with. So what do we have for the y value here? All right, Maria, I see your answer. So we're trying to get the y by itself. Jen, okay, very nice. So cancel out the 46, move it to the other side. You're left behind with negative y. This, of course, ends up becoming -5. And then since you have negative on both sides, multiply or divide by -1. And you end up getting y equals 5. Alrighty, perfect. So now we have both x and y, which means we can now go back to the original variable we eliminated and find the z. Now for the z, you of course need to go back to one of the very original equations. So anyone from the 1, 2, or 3. And I'm thinking, you know what, let's just use equation 1. So 7x minus y plus z equals 5. All right, so we have x equals 2, y equals 5. So what will that z value come out to be? All right, Della, I see your answer. Maria, okay. So let's take a look here, guys. You have 7 times 2, which would be 14. 14 minus 5 plus z equals 5. Of course, 14 minus 5 would be what, 9? Yeah, very nice. So yeah, when you subtract the 9, move it to the other side, we end up getting z equals -4. So our ordered triple is going to look like 2 for the x value, 5 for the y value, and then looks like -4 for the z value. All right, Jen, I see your answer. Perfect. So the last thing you really want to do is just check and make sure this will be a solution for all 3 of our original equations. So for the first one, we had 7x minus y plus z equals 5. So we'll need to check in that one. For the second one, we have 2x plus 2y minus 3z equals 26. And then the last one is x minus 3y plus 2z equals -21. So let's start with the first one. 7 times 2 minus 5 plus -4. And we want to get a true statement here. So of course, we just did this math. So that will be 14 minus 5. Positive and negative ends up becoming -4. 14 minus 5 is 9. 9 minus 4, of course, gives us 5. So true statement for the first one, it is definitely satisfying the first equation. Now for the second one, again, 2 times x plus 2 times y minus 3 times z. And you want to make sure this will equal to 26. So let's see, what will this guy come out to be? 2 times 2 is 4, 5 times 2 is 10, negative, and negative will become positive. 3 times 4 is 12. So let's see, 14, what will that be? 24, 26. All right, very good. So we get a true statement for the second equation. Now just the last one. we've got x minus 3 times y plus 2 times z, and that should equal 21. So 2 minus 3 times 5, of course, is 15. Positive and negative will give us negative. 4 times 2 is 8. And what will that be? 2 minus 15 is what? Negative 13. From that, we are subtracting 8, which will, of course, end up giving us, oh, sorry, that's negative 21, and I didn't put the negative there. Negative 21. There we go. And that makes sense because then negative 13 and negative 8 ends up giving us negative 21 also, and you are getting a true statement for the third one. So once all three of them give you a true statement, we know we have found our solution set, which is going to be the ordered pair 2, 5, negative 4. So this one obviously is an independent system, and it's telling us all three of those planes are meeting at exactly one single point, and that's what we ended up with. So let's plug that answer in. So that will be one solution, and that is 2, oh, come on, 2, 5, negative 4. There we go. Okay, and we are good to go. Questions on this example here, guys? Everybody okay? And I know it will take like a little practice for you to feel comfortable with this, but just any questions kind of popping up as we went through the example. Okay, so a slightly different one because you have two equations with 3 variables. So let's get back up here. Okay, so here we're talking about what would it look like if you had infinite number of solutions. So in this case, we are saying, what if you have only 2 planes, which are in the 3-dimensional space? So if you have only 2 planes in the 3-dimensional space, they can either be parallel to each other or they will intersect along a line. So imagine what would happen if you took, 2 pieces of paper, since we're kind of comparing it to a paper, and, join them in different configurations. And you can see that kind of in the figure we have down here. So let's try and get that. So you can kind of see how these two page on the left-hand side are intersecting, and they're only two planes, but you will see the way they are intersecting is exactly at that one single line. But since these papers, keep going in all direction, this plane is basically an infinite space. That line is also going to be a line which is going to be infinitely long, which means you will end up with infinitely many solutions, basically. So that would be with 2 planes if they're intersecting, but you can kind of see that on the right-hand side with the 3 planes also. So even if you had 3 planes intersecting, they can still intersect at that one single line. So that is possible with 2 equations or with 3 equations. So we're kind of talking about, okay, if the planes are going to be intersecting and there's only 2 of them, they can intersect along a line, which means you will end up with infinitely many solutions, which will satisfy both your equations. However, if the 2 planes are going to be parallel to each other, then obviously that means they're running right alongside each other, right? Kind of like, 2 walls in a hallway, they're always going to be parallel to each other. So you will have no common point, which also means there will be no solution to that system. So those would be, the 2 options that can happen if you have 2 planes in a 3-dimensional space. So in that case, your system could actually just have 2 equations with 3 variables. And how would we go about solving this. So of course, the idea here is we're kind of talking about a line in a three-dimensional space does not have a simple equation like a line in a two-dimensional, coordinate system, like your y equals mx plus d kind of equation. It wouldn't be as simple as that when you're looking at a 3D space. So in this example, your basically answer comes out looking like this. So you're not going to have a simple, 2, -3, 5 as your answer in this case, because you have infinitely many solutions. So you are going to actually end up with your answer in a more generic form where you will have at least one variable as part of your answer. So you can either have the x, the y, or the z variable as part of your answer. So if you have, x, your x value will be just the letter x, but then your y and z are going to be dependent on the x values. If you were to write it as something with y, then you would have, y something something here. The middle would just be y by itself, and then for the z, this would again be, y something. If you were going to write all of your answers with z, then you would have z over here, but then this would be, z something, and some kind of z expression in the middle term also. So just imagine, if we were to rewrite it instead of x in y on z, what would those ordered triples end up looking like? So there's kind of just talking about, yes, you can actually say, since you have infinitely many solutions, these points will satisfy both your equations, and they're going to lie on that, single line where the two planes are intersecting. But these are only 3 answers out of all the infinite options you have. And so that's why you want to write it in this form and not just as, simple ordered triples. So let's take a look at how we can solve an equation like this. So let's go back to my MATLAB here, and let's copy this guy over. So this is number 3, which is 5.2.29. And we are given x minus 3y plus 13z equals 9. And 2x minus y plus 4z equals 5. So you're starting out the same way like we did the previous example here, guys. Pick either x, y, or z to eliminate. So which one do you think might be an easier variable for us to get rid of? X, y, or z? Okay, Della, you are suggesting x, and yeah, we can do that. We can get rid of x. So what would we need to do to eliminate x? How would we achieve that? Yeah, so since you're getting rid of x, you have x on the first equation, 2x on the second one. So you need to have, positive 2x and negative 2x to eliminate it. So we need to multiply the first equation by -2. And then, of course, add it to equation 2. Okay. So let's see, if we're multiplying the first equation by -2, what are we going to end up with here, guys, when we rewrite that equation 1? So multiply that first equation by -2, and what are we looking at? Okay, Della, remember you're multiplying on the right-hand side also. So let's see here. Your negative 2x looks good. Maria, yeah. Negative 2x, and then negative 3y times negative 2 will be positive 6y. Jen, I think that looks good. Of course, positive 13z with negative 2 will end up becoming negative 26z. And then on the right-hand side, 9 times negative 2 will give us negative 18. We're keeping the second equation as it is. And then we will, of course, end up adding these guys together. So your x is what we wanted to eliminate. So that guy disappears. And then remaining, we are left with, let's see, 5y. What will this be? Negative 22z equals, what's that? Negative 13. I actually just realized something. How do they want us to write this? Okay, so we know we are going to end up with more than likely infinite number of solutions. So that's going to be these two options, infinitely many solutions. And you can see this one is giving you x is any real number, which means we would put x over here. And then these two guys would be, x something in the expression. This one over here seems to be using a set builder notation. But I'm not sure if it wants us to put the answer in that format. I think normally they go for that second one. So we want to make sure we write everything in terms of x. So let's take a look at, so here, we're ending up with 5y minus 22z equals negative 13. We probably should not have eliminated x then in that case, since they wanted us to write the answer in terms of x. Okay, let's come back over here for a minute and see what happens if we choose option C over here. I don't think they accept that, but I want to try it out. You will see how this guy is ending in a 9, which means this is the equation you are looking at, because that also ends in a 9. So I'm going to try typing these coefficients in and see what happens. So your x value is 1 in that equation. Your y value is negative 3. And our z value was 13. Yeah, see, I didn't think they were going to choose that option. So you have now, seen that this is not going to work. So we definitely want to go for this one. And that means since we have to write our answers in terms of x, unfortunately, that means we want to keep the x and we don't want to get rid of it. So since we cannot do x, what other variable can we eliminate instead of x? So I'm actually going to erase this. Yeah, so you either want to pick y or z, since we want to keep the x in our answer. So you are suggesting y. So let's go ahead and eliminate y. So to eliminate y now, what would you change here? What would we need to modify our equation so that we can get rid of y? Yeah, Della, very nice. Eliminate by multiplying your second equation by negative 3. Very nice. So because since this guy is negative 3, we want the second one to be positive 3. And for that, we will need to multiply this guy by negative 3. So we are multiplying equation 2 by -3, and then we are adding equation 1. Alrighty. So equation 1 will stay the same, x minus 3y plus 13z equals 9. And then let's see, this guy will end up becoming -3. So that would be what? -6x. Negative would become +3y, which is what we wanted. -3 and +4 will give us negative, what is that, 12z. And then -15 on the other side. All right, now we are ready to add these guys together. So now you will see when we combine these, our y cancels out. X will stay back, which is what we wanted again. So this guy would be -5x over here. Plus 13 minus 12 will, of course, just give us +1z. And then 9 minus 15 will end up giving us what? -6. Okay, this is what we were looking for. So now we can actually rewrite this where you will put z in terms of x, which means get the z by itself and move your x term to the other side. So now we can go ahead and add x, or in this case, 5x to the other side. And we end up getting z equals +5x minus 6. Now we want to do the same thing for the y variable. So for the y, take any one of the equations, it doesn't matter. Maybe the second equation. Okay, our second equation is 2x minus y plus 4z equals 5. So the x will stay as it is, the y will stay as it is, but z is where you're going to use substitution and replace z with what you just found out, which is the 5x minus 6. And then, of course, you have 5 on the other side. So what we're basically doing is we're taking our z and replacing it with the value we just came up with, and that's the 5x minus 6. So the idea is you want to isolate the y now, like we did with the z, and move all the other terms, the x terms, the constant terms, to the other side. So let's clean this guy up. You have 2x minus y plus, and then, of course, you're going to distribute that 4 inside the parentheses. Which will end up giving us what? 4 times 5? 20x. And then, of course, 4 times 6 is 24. So can you tell me, once you get the y by itself on one side and move all the other terms to the other side, what it will end up looking like? Y equals what? It looks like we've got Della, okay. So we can combine our like terms first before you start moving things over. So plus 2x plus 20x, yeah, very nice. Minus y minus 24 equals 5. So what are you guys getting for just y when you get y by itself and move everything else to the other side? Yeah, Della, your answer looks good. Very nice. So clean that up. And what does your y value come out to be? Maria, very good, very nice, perfect. Okay, so we want to move the y. Now you can move the other terms, but I think it'll be easier for us to just move the y to the other side. And then, of course, you can bring this 5 over to the left-hand side. And so we will end up with 22x will stay, the y is gone, this guy ends up becoming negative 29, and then just y on the other side. So this is what we were looking for. So your solution set, of course, we know there are infinitely many solutions. And then our triple will be just x for the x variable. Your y, as you see, just came out to be 22x minus 29. And then, of course, we found z at the very first stage, which was 5x minus 6. So that'll go for the z. All righty, let's plug this in. So second option, you will have x for the x variable. 22x minus 29 is what we got for the y variable. And then z was 5x minus 6. There we go. And let's check this guy. And you will see that is the answer that they wanted us to come up with. Questions on this one here, guys? So normally when you are looking at a system like this, where you only have 2 equations in 3 variables, that normally means you are going to end up with either the 2 planes being parallel, which means you will have no solution, or like we saw in this example, you end up with infinitely many solutions. And then what I tell you guys to do here is look at the answer option before you start solving it and see which variable they're keeping in the answer. If they're keeping x over here, then you don't want to eliminate the x. Sometimes you will also see z over here. So if you see z over here, then that means you don't want to eliminate the z. So before you start solving, look at which variable they're keeping in the answer, and that will tell you don't eliminate that variable. So that's kind of what we were going for over here. All righty, let's come back to our handout. So this one over here is kind of talking about, again, what if you had something like this situation where you have 3 planes that are intersecting at, again, one single straight line, which means you again end up with infinitely many solutions along that line of intersection. And that would be something like example 4 over here. So in this example, you are actually using the set builder notation. So in this case, you would definitely end up writing your equation like this, where, we basically took the first equation and we're using that in our answer option. But you can definitely do that with equations 2 and 3 also. So the idea here is if all the equations are equivalent, you will end up with a solution set where, all the ordered triples, if they satisfy one equation, they'll satisfy all 3 of them. And this is where we would use this set builder notation. But as you saw in the example we just did, they wanted us to do it specifically in terms of x. Sometimes they will have y, sometimes they will have z, but they don't want us to use, this kind of notation in that example. So it just kind of varies from example to example. Now, when we're talking about an inconsistent system, this of course means you have no solution. And I think this was a pretty neat illustration to show you that, 2 of the planes are intersecting. So we can definitely see like these 2 planes are intersecting over here. or this one at the bottom with the one on the left is intersecting here, or the bottom and the right is intersecting here, but all three of them don't have a single point which is common between all three of them. And that's why you are ending up with no solution, because we want all three of the planes, in whatever order they are placed, to have at least one point which would be common, kind of like we saw in that first example over here, that you at least had one point of intersection. But if you don't have something like that, then we would say our system is inconsistent, and basically you have no solution in that case. And so how would we go about solving a system like this? So let's take an example, and I believe the one we are looking at might be an example for an inconsistent system. So let's take a look at this guy here. So this one is number 4, 5.2.37. Alrighty, we are given 3x plus 3y plus 4z equals -2, 9x plus 9y plus 12z equals -9, and then 2x minus 3y plus 3z equals 4. So you're going to do this like the very first example we did. We want to take it from 3 equations, 3 variables, down to 2 equations, 2 variables. So in this case, just in case we end up with infinite many solutions, which I'm not sure we will, but since they are asking us to keep the z variable, let's not eliminate z just in case. I have a feeling it should be option C as the answer, but I'm not sure till we solve it. Honestly, it could end up becoming option 1 also, but just to be on the safe side, since they want us to keep z over here, let's save the z and not eliminate it. So except z, what can we do if you wanted to eliminate x or y? Which one would you choose? Do you want to get rid of x, or you want to get rid of y? Which one, I suppose, would be easier? Okay, Della, you're saying y, so let's eliminate y. And to eliminate y, what would we need to do? And again, remember, you can do the combination of equation 1 and 2, equation 2 and 3, equation 1 and 3, however that works out. So which 2 equations would you combine, and what math would we need to do? All right, Jen, you are saying use equations 1 and 3. And since you are eliminating y, we don't need to make any changes, right, to 1 and 3, because you already have the +3 and -3 on your y value. So honestly, just add equations 1 and 3. So that is 3x plus 3y plus 4z equals -2. And then 2x minus 3y plus 3z equals 4. So just adding them together, our y variables will cancel out. 3 plus 2 will give us 5x. Of course, 4 plus 3 will give us 7z. And then let's see, -2 plus 4 will, of course, end up giving us 2. And we will call this guy equation 4. Okay, so we did equations 1 and 3. Now we need to use equation 2 with what? 1 or 3? Which one would you go for? Okay, you guys want to do equation 3? That's fine. What would we need to modify to get equations 2 and 3 combined together? What would you do? Multiply by 3. Yeah, Della, very nice. So we will take our third equation and multiply it by 3. So equation 2 will stay the same. So that's 9x plus 9y plus 12z equals -9. So you are multiplying equation 3 by 3, and then you're basically adding it to equation 2. Okay, so equation 2, 9x, 9y, 12z minus 9, all of that stays the same. And then let's see, multiplying by 3. So 3 times 2 will give us 6x, minus 3 times 3 is 9y, 3 times 3 is 9z, 4 times 3 will give us 12. And now you're adding this together. So let's see, positive 9y, negative 9y cancel out as we wanted it to. 9 plus 6 will be what, 15x? Plus, what is that? 12 plus 9 is what, 21z? And then -9 plus 12 will give us 3. All right, so we have now taken this from 3 equations, 3 variables, to 2 equations, 2 variables. So now let's go ahead and see what this guy comes out to be. 5x plus 7z equals 2. This is equation 4. And then we had 15x plus 21z equals 3. This will be equation 5. And again, like I was telling you before, since they're kind of asking us to keep z available, let's not get rid of z and let's get rid of x. So what would you do to eliminate the x? So what kind of calculation would we need to do so we can get rid of x? Yeah, Jen, very nice. And which equation are you multiplying by -3? Very good. Yeah, you multiply equation 4 by -3, so we can turn that into -15x. So multiply equation 4 by -3, and then of course add it to equation 5. Okay, so that will end up giving us, let's see, -15x. What's that? -21z. All right, Della, I see your answer. And then this guy will be, what is it, -6. Keeping the equation 5 as it is, so 15x plus 21z equals 3. And then when we add this together, -15x, +15x is canceling out. Yeah, -21z, +21z is also canceling out. So you end up with 0 equals -3, which of course we know they are not equal. And you are ending up with a false statement. So what does that tell us, guys, when we end up with a false statement like this? Because we didn't get an answer for z as we were hoping it would be. But instead we ended up, of course, we eliminated y. Now your x and z also canceled out. So all your variables are gone. Yeah, this is what happens when you have an inconsistent system with no solution. Very nice. So as I was hoping, it would end up giving us empty set as our answer because we have no solution. So let's write that over here. It's an empty set. And let's check this guy. All right. Any questions on this example here, folks? So we saw how you can find an independent solution where you get one order triple. That was that first example we did over here where we got this as our solution. Then in the second one, you got to see what happens if you have infinitely many solutions and how you write out that order triple. And then now for this last one, we ended up seeing what would happen if you had an empty set. And this is what we end up with over here. Now, the last part, and we will have to do this obviously next time, is an application of how do we use the system of equations in 3 variables to actually help us find the equation of a parabola. So that's kind of where you will see one of the uses of this method over here. So that's where we'll pick up for our class on Thursday. And we will, talk about how to find an example like this. And that's pretty much the last part that we need to focus on for this section 5.2. And then we'll get into section 5.3. So we should be able to finish chapter 5 on Thursday. And then on Thursday, when we're in class, we can talk about kind of what we're doing with chapter 5 exam. More than likely, it's probably going to be a take-home exam because we don't really have class time to do that exam in class. It's going to be a very short exam since you're only doing 2 sections, 5.2 and 5.3. So we'll probably do that as a take-home exam. And then the following Monday, we'll just do a quick review on chapter 7 and basically wrap up for the semester. So that's kind of where, we'll kind of take this class at. So any questions as we're kind of talking about, this week and next week? Now, remember, you do have the practice final exam available in my math lab. If you guys wanted to start looking at, the material we've covered at the beginning part of the semester, anything you want to review, all of those types of questions you will see in the practice final exam. It's not for a grade. It's just, yeah, Della, we can definitely do that. So it's not for a grade, just as a practice to get you guys ready for the final exam. So just start looking at that when you have time, but at least start working through section 5.2 homework if you can before class on Thursday. So that way, if you're stuck on anything and you need help, you can ask me on Thursday. And hopefully, we'll be back on campus on Thursday and the snow will be gone and it'll be, good for us to get back. Yeah. So no exam for chapter 7. You will just have questions from chapter 7 on your final, but not a specific exam for chapter 7. Because like I said, we're just going to focus on the material that they want us to cover, and we're going to leave all the extra stuff out. So we won't do a chapter 7 exam. Okay. All right, guys. I know Della said she wanted to stay back and ask me any question, but if anybody else also has a question and you want to stay back, I'll be happy to answer that. And then I'll see you guys on Thursday. So good luck, everyone. Stay safe and have a wonderful day. Take care, guys. Be careful. Hey, Della.